Good afternoon, dear children. Let us start our new chapter, linear programming. Can you hear? Okay, so let us start the chapter linear programming. This is an application of the chapter linear inequalities which you had learnt in your 11th standard. Okay, linear inequalities. So, first let us have some new terms here. Of that, the first one is an objective function. Objective function. A linear function z is equal to ax plus by, where a and b are constants which is to be maximized or minimized, or minimized, is called a linear objective function. Is it clear now? Is there any problem in audio? Okay, 1 minute. So a linear function What about the sound now? Is it clear? Okay, now a linear function z is equal to ax plus by, where a and b are constants which is to be maximized or minimized is called a linear objective function. Now is it okay? Okay, now see, we are given a function z is equal to ax plus by, where a and b are constants and x and y are variables. So these type of functions are called objective functions. This is the first term you have to learn here. Objective function. What is to be minimized or maximized? Represent it as a function and it is called an objective function. It is called an objective function. The variables x and y are called decision variables. X and y are called decision variables. This is the second term. The variables involved in this objective function, the variables which make the objective function are known as decision variables. Variables x and y are called decision variables. Now the next one is the linear inequalities. The linear inequalities or equations. The linear inequalities or equations which represent the restrictions on variables are called linear constraints. Are called linear constraints. Are called linear constraints. The linear inequalities or the equations which represent the restrictions on variables are called linear constraints. linear constraints. See, this is the objective function which we have to maximize or minimize. Some conditions must be given to us for these variables. The variables have to satisfy some conditions, and that conditions may be as inequalities or equations. They are known as linear constraints. The conditions x greater than or equal to 0, y greater than or equal to 0 are called non-negative constraints. So this is the second term here, linear constraints and non-negative constraints. See, we are given a function which is to be maximized or minimized subject to certain conditions, and the function to be maximized or minimized is called the objective function. The variables involved in this objective function are called decision variables. The conditions to be satisfied by the variables x and y are called linear constraints, and in all these cases the condition x greater than or equal to 0, y greater than or equal to 0. That means the variables must be non-negative always. Okay, these are known as non-negative constraints. Now the third one is a linear programming problem. A linear programming problem is one that deals with finding the optimal value of the objective function subject to the constraints, including the non-negative constraints. So a linear programming problem is a problem in which we have to find the optimal value. Optimal value means maximum value or minimum value of the objective function subject to the given conditions, and that conditions are called constraints, and that also include the non-negative constraints. That means the variables are always non-negative. This is called a linear programming problem, or we can write this as LPP, a linear programming problem. And here in this chapter, there are three different types of linear programming problems. First one is diet problem. Second one is manufacturing problems. And the third one is transportation problems. In this chapter, we have to learn these three different types of problems. First one is diet problem, second one is manufacturing problems, and the third one is transportation problems. And now the next is solving a linear programming problem. Solving a linear programming problem by graphical method. This is what you have to learn in this chapter. Solving a linear programming problem by graphical method. First step is to find the feasible region. To find the feasible region. Feasible region, or this can be solution region. You can say this as solution region, feasible region or solution region. To find the feasible region, we have to draw the graph of the linear constraints, then the common region determined by all the constraints the common region determined by all the constraints including non-negative constraints. Including non-negative constraints is called feasible region. Feasible region. So feasible region means it is the common region determined by all the constraints including non-negative constraints. That means we have to draw the graph of all the inequalities or equations, and you have to find out the common region of all those. Then points within and on the boundary of the feasible region represent the feasible solution. You have to be familiar with these terms: feasible region, then the feasible solution, the points within and on the boundary of the feasible region are called feasible solution. Then any point in the feasible region, that gives the maximum or minimum value, the minimum or maximum value of Z, the objective function, is called an optimal solution. Is called an optimal solution. And this is another term, optimal solution. See here, we are given a function z is equal to ax plus by, and some conditions are given to us. That conditions may be linear inequalities or equations, and the non-negative conditions will also be there, x greater than or equal to 0, y greater than or equal to 0. And using these conditions, we have to solve the given problem. That is what we have to do. For that, we are using graphical method. And in graph, we have to draw the graph of the inequalities. That means the linear constraints. We have to draw the graph of the linear constraints or the linear inequalities which are given in the question. And then we have to find the feasible region. That means the common region satisfied by all these linear inequalities. And then you have to find the maximum or minimum value of z in that region. That is what we are going to do in this linear programming. Okay, let us have one question. By solving it, these terms will be clear to you. Exercise 12.1. And one more thing, here in this, two different types of problems are there. One, when the feasible region is bounded, and when the feasible region is unbounded. See, unbounded, when we are getting an unbounded region, it is the deleted topic from the syllabus. No need to find the unbounded region here, only problems in which bounded region are as feasible region, we have to solve the problems. Okay, let us see how it is. Maximize, first question, maximize z is equal to 3x plus 4y subject to the constraints x plus y less than or equal to 4, x greater than or equal to 0, y greater than or equal to 0. See, maximize z is equal to 3x plus 4y subject to x plus y less than or equal to 4, x greater than or equal to 0, y greater than or equal to 0. Here we have to maximize z is equal to, so this is the objective function. This is the objective function, and the linear constraints given here, only one condition is given to us, and this is called the linear constraint. These are the non-negative constraints. Non-negative constraints. Okay, these are the terms which we defined. Is it clear now? What is objective function? What is a linear constraint? What are non-negative constraints? Is it clear? Okay, so now what we have to do is we have to draw the graph of this linear constraint. Okay, here only one condition is given to us, and we have to draw the graph of this. First we have to consider this as an equation to draw the graph. Okay, x plus y is equal to 4. This you had learnt in your 11th standard, how to draw the graph of a linear inequality. First we have to consider the equation corresponding to it, find the table of values to draw the graph. This x, y, when x is equal to 0, y is equal to 4. When y is equal to 0, x is equal to 4. Draw the graph of x plus y is equal to 4. So you can draw it in a graph paper. This be 0, 4 and here 4, 0. This line divides the plane into two halves. One is the upper half and the other one is the lower half. You have to find which half plane represent x plus y less than or equal to 4. The upper half plane or the lower half plane. Which one is the solution region for this x plus y less than or equal to 4? Upper part of this line or the lower part? Which is the solution region? How you are finding it? See, consider a point. For our convenience, let us take 0, 0, the origin, and put the values for x and y here. X plus y less than or equal to 4. X is equal to 0. Y is equal to 0. So if this statement is true, that is 0 less than or equal to 4. If this statement is true, then the half plane which contains the origin is the solution region. Half plane which contains the origin is the solution region. So which is the half plane here? Lower half plane or upper half plane? Give your answer. It is the lower half plane. So this lower half plane is the solution region for this inequality. And two more things you have to consider here. See, x greater than or equal to 0, y greater than or equal to 0. This means x and y are both non-negative. Non-negative means it is in the first quadrant. So all these three conditions to be satisfied. Okay. The lower half plane for this and in the first quadrant. This means in the first quadrant region only we have to consider. So you have to shade the common region. This is the common region for which satisfies all these three conditions. So it's a triangle here. Always you have to consider the common region for all these conditions. So here x plus y less than or equal to 4 means the lower half plane of this, and that must be in the first quadrant. Now the next step is, so the first part is over now. To draw this one you have to use the graph paper, then it will be neat. And now we have to find the corner points of this shaded region. So which are the corner points here? Corner points. This is the second step. First point is this one, second point is this one, and the third point is this. So which are the corner points? 0, 0. Origin is one point here. This is another point and it is 4, 0. And the third one is 0, 4. Is this clear? Okay, now we have to find the value of z. Z is given as 3x plus 4y, that is the objective function is given to us 3x plus 4y. You have to find the value of z at these points. That means put the value of x as 0, y as 0, find the value of z. Put x is equal to 4 and y is equal to 0, find the value of z. Put x is equal to 0 and y is equal to 4, find the value of z. So when you put 0, 0, value of z becomes 0. What about the other two values? (12 and 16). 12 and 16. So which is the maximum value here? Which is the maximum value of z? It is 16. See, our question is maximize z. Okay, so the maximum value of z, maximum value of z is 16 when x is equal to 0 and y is equal to 4. This is the solution. This shaded region is called the feasible region. Only this much we have to do. The first step is you have to draw the graph. Then find the feasible region here. Feasible region means common region for all the constraints given to us. And then find the corner points. Find the value of the objective function at the corner points. The maximum value gives maximum of z and the minimum value is the minimum of z. And you have to write the value of x and y at that point. Is the method clear to you? So the terms once again here: objective function, linear constraints, non-negative constraints, then x and y are called the decision variables. The common region is called the feasible region. Or solution region, and this gives the solution of the linear programming problem. Okay, try one more question. Minimize z is equal to minus 3x plus 4y subject to x plus 2y less than or equal to 8, 3x plus 2y less than or equal to 12, x greater than or equal to 0, y greater than or equal to 0. Even if this is not given there, you have to take this condition. This is a very important part of this LPP. Non-negative constraints. The variables must always be non-negative. Okay, now try to draw the graph and give the corner points. Table of values for this. First one is x plus y is equal to 8. Sorry, this question is x plus 2y less than or equal to 8. X plus 2y less than or equal to 8. Please make this change. X plus 2y less than or equal to 8. When x is equal to 0, y is equal to 4, and when y is equal to 0, x is equal to 8. 0, 4 is 1 point and 8, 0 is another point. This is x plus 2y equal to 8. And now the second one is 3x plus 2y equal to 12. The table of values here. xy, when x is equal to 0, y becomes 6, and y is equal to 0, x is equal to 4. So it is 4, 0 and 0, 6. So this is the graph of 3x plus 2y is equal to 12. Now you have to find out the feasible region. That means the common region for all these constraints. X greater than or equal to 0, y greater than or equal to 0. So that must be in the first quadrant. And which half plane here? The lower half plane or upper half plane? Which part is to be shaded here? Why it is the upper half plane? Do you mean this one? This part? See now when we consider this, listen here, x plus 2y is equal to 8. When we consider this line, which half plane? That means this is the upper half plane here and this is the lower half plane. Which half plane is the solution region for this one inequality? X plus 2y less than or equal to 8. How we are considering it? How we have to consider find the solution region? See now, take a point in any of these planes and it is easy for us to consider the origin. Okay, so we are considering origin here. X plus 2y less than or equal to 8 is the inequality given to us. Put x is equal to 0, y is equal to 0. So you will get 0 plus 0 less than or equal to 8. That is 0 less than or equal to 8. If this statement is true, then you have to shade the region which contains the origin. So which is the plane here? Upper half plane or lower half plane? See, this line divides the plane into two. Okay, this part is one and this part is the other one. We are considering a point 0, 0 from this plane. 0, 0. And we substitute the values here. if this statement is true, then you have to consider the plane where the 0 is included. If this is true, if this is false, then we have to consider its opposite part. Is there any doubt? Afrin, which half plane we have is the solution region here? For this equation, x plus 2y less than or equal to 8. Please give your answer. Tejas. The shaded region is this lower half plane. For this line and for this line, both these lines, the lower half plane gives the solution region. Okay, see, if we consider the second one, this is 3x plus 2y less than or equal to 12. 3x plus 2y less than or equal to 12 is this line, and we are considering origin from this side. So if we put 0, 0, it becomes 0 less than or equal to 12. This is a true statement. So the plane containing the origin is the solution region. So the shaded portion that is common for both these. Common for both these is this quadrilateral. Okay, we have to shade this region. Is this clear now? Any confusion in upper half plane and lower half plane? I think you are considering this x-axis and y-axis and hence saying this as upper half plane. Isn't it? See, now we are considering separate lines. We have to consider the lines here and then to shade the region. Okay, now you have to find the corner points. The next step is to find the corner points and then the corresponding value of Z. So which are the corner points here? Which is this one? Give the corner points 0, 0. First one. What about this? Here it is 0, 4. Okay, it is 0, 4. What about this point? It is for the second line. Second line y coordinate is 0. It is 4, 0. 4, 0. And now we have to find out this point. This point is the intersection of the two lines. Okay, see now. This corner point is the intersection of the two lines. If you are drawing this in a graph sheet, you can identify it from the graph paper itself. Okay, otherwise we can solve these two equations. X plus 2y is equal to 8 and 3x plus 2y is equal to 12. Solve these two pair of linear equations by elimination method or any one method. You can solve this and find the value of x and y. Multiplying this equation with 3. Coefficients will be the same, then subtract it and get the value. Solve this for x and y. Okay, y is equal to 3. We will get the value of y as 3 and then x is equal to x is equal to 2. Okay, so the corner point is 2, 3. Okay, so you got all the 4 corner points here. Find the corresponding values of z. Find the corresponding values of z. First one is 0. Second one, (16). Okay, now the third. It is -12, right? Then fourth one is it is 6. Okay, so which is the minimum value of z? Question is minimize z is equal to. So which is the minimum value here? -12 when x is equal to 4 and y is equal to 0. This is the optimal solution. Is it clear? Okay, see, listen now. Sometimes we are getting the shaded region here. that means it is unbounded. It is not bounded here. You will get the solution region like this. So that topic is deleted from the syllabus. So question number 4 and 6 in 12.1 are such questions. So we can remove that questions. Question number 4 and 6. So you try the third and fifth question. Third and fifth question from 12.1. And if you have any doubt, please give me a message. I will once again explain it in the next class. Okay, try that two questions. Third and fifth question from exercise 12.1. Okay, now the next one is show that the minimum of Z occurs at more than 2 points. Show that the minimum of Z occurs at more than 2 points. In first one, minimize and maximize Z is equal to 5x plus 10y, 5x plus 10y subject to x plus 2y less than or equal to 120, x plus y is greater than or equal to 60, x minus 2y greater than or equal to 0, x y greater than or equal to 0. Minimize and maximize, both we have to find. Z is equal to 5x plus 10y subject to x plus 2y less than or equal to 120, x plus y greater than or equal to 60, x minus 2y greater than or equal to 0 and xy greater than or equal to 0. Same procedure, you have to draw the graph of all these constraints. So the first one is x plus 2y is equal to 120. And x is equal to 0, y becomes 60, and y is equal to 0, x is 120. Then the second one is x plus y is equal to 60. For this, x0, y60, y0, x60. And the third one is when x is equal to 0, y is also equal to 0, Then you have to give some other values. Then x is equal to x is equal to 120 or 60 we can give here. Here two values are there. So let us give 120. Y is equal to 60. So you can draw the graph. This be 60 and 120. So this be x plus 2y is equal to 120. Then 60, 0, 60 and 60, 0. This will give another one. This one is x plus y is equal to 60. And now the third is 0, 0 and 120, 60. 120, 60 is here. So it's a line like this. Now we have to find the solution region for this. So it is x plus 2y less than or equal to 120. It is this is the first line. So when we consider 0, 0 here, 0, 0, the statement will be true. So the lower part of this is to be considered. Keep in mind, the lower part of this line is to be considered here. For this second one, this is the second line, x plus y greater than or equal to 60. So here, if we consider 0, 0 here, x plus y greater than or equal to 60. When we put 0, 0, 0 greater than or equal to 60 is a false statement. This is a false statement. So we cannot consider the half plane containing the origin. Its opposite part we have to consider. Okay, for this first line, the lower part. For this, the upper part. And now we have to consider this line. That is x minus 2y is equal to 0. This is x minus 2y equal to 0. We cannot consider the origin here because this line passes through the origin. So you have to consider any other point. Let us take this 0, 60. See, x minus 2y greater than or equal to 0. If we put 0, 60, this point 0, 60. So 0 minus 2 into 60, it is 120 greater than or equal to 0. 120 greater than or equal to 0. This is a false statement. Minus 120 is greater than or equal to 0 is a false statement. So we cannot consider the plane containing this point. Its opposite part we have to take. Okay, so for the first one, the lower half. For the second one, the upper part. And for this, the lower part. So the common region is this one. Is it clear? Did you get the same region? Okay, then next step is to find the corner points. Which are the corner points here? This is 60, 0. See now the second line, y coordinate is 0 at 60, 0. So this point is 60, 0. To find out this one, it is 120, 0. Now you have to find out these 2 points. X plus 2y equal to 120 and x minus 2y equal to 0. Solve these two. X plus 2y equal to 120 and x minus 2y equal to 0. Solve this and find the value of x and y. X 60 and y 30. Okay. 60, 30 is another corner point. Now you have to find out this also. That is, you have to solve x plus y is equal to 60 and x minus 2y is equal to 0. That is these two lines. Okay, y 20 and corresponding x is Janaki, it is not 20, 40, x value first and then y value. It is 40, 20. Always write the x value first and then the y value. Now find the corresponding value of z. 5x plus 10y in each case. Find the value of z in each case. Okay, the first one is 300. Then what about the second? $600. Okay. Third one. Friend, check it once again. 5 into 60. Third, 300 plus 300. 300 plus 300. That also gives the answer 600. Right? Okay, last one is 400. So here, which is the minimum value? Which is the minimum value in this? Minimum value is 300. So you have to write the minimum value is 300. You can conclude it. Minimum value of Z is 300 when X is equal to 60 and Y is equal to 0. What about the maximum value? Maximum value occurs in these 2 points. See 120, 0 and 60, 30. See 60, 30 is this point. 60, 30 is this point and 120, 0 is this point. This means that, see, if you get an answer like this, if more than 2 points are there, the question show that the minimum or maximum of Z occurs at more than 2 points. This is what we have to prove here. See now, if you are getting an answer like this, in this question it is okay, it is show that, but otherwise the question is minimize or maximize. You have to conclude the answer as the maximum value of Z is 600. Maximum Z is 600 when, see the value of X here, it lies between 60 to, it lies from 60 to 120. So you can write when 60 less than or equal to X less than or equal to 120. That means X lies between 60 and 120 and Y lies between 0 and 30. 0 less than or equal to Y less than or equal to 30. This is the solution. Maximum occurs at these 2 points. So you have to conclude your answer like this. Is it clear? So I hope the graphical method of solving linear programming problems clear to you. The remaining questions we will do in the next class. Thank you.